All right, let's get started. Hello, Pranav. I think more people will soon join.
Yep, yes, sir.
Okay.
Oh, yeah,
Thanks for
there's
joining.
no one. The first one to join.
That's all right. Okay, so I think more people will join soon. Maybe we'll get started. Uh, so feel free to give your answers whenever you whenever you need it. Before we start, do you have any questions you wanted to ask me? Let me check my recordings. Okay.
Just let me check. Maybe, I may have.
Could you repeat? I couldn't get it.
No, I was actually going to check how,
Okay,
if
okay.
I if I may have it.
Sure, sure. No problem. So I welcome other people also here. We have Ram sir and Tanisha. Before we begin today, I was asking whether you have any questions. Uh, would you like anything to address first? All right. So if there are no questions, let's begin today's class. Sir, Ram sir, are you? Do you have any questions?
No, I will ask in the end. And
Sure,
this
sure.
is
Yeah.
related to the segment
Okay.
one which has already worked.
Okay. Okay. Sure, sure. You can ask me at the end. Today's question is simple only. I will complete it soon. Uh, so I have one question regarding the liquid propulsion, and also I have something interesting to show you. So I have, as I said last week, I will show you some technique which you can use it to find chamber temperature, C star and ISP, instead of calculating your own by hand. So but now that is going to be out of scope for this course, but I thought it's an essential skill if you are thinking of a career in this field. Okay, so we'll discuss more about this. Before that, we'll solve this question here. um, so what do we have here is 16. So we have a liquid rocket engine here, um, which is a pump fed liquid rocket engine which uses liquid methane as a fuel and liquid oxygen as a oxidizer. Okay, the engine produces, I'm sorry, okay, so the engine produces thrust of 3000 kilonewton over a burn duration of 120 seconds. Okay, so the engine is producing 3000 kilonewtons and it is going to be active for a burn duration of 120 seconds. The propellants are fed into the combustion chamber at a pressure of 6.4 megapascal, which is the chamber pressure, using a separate high pressure pumps for liquid methane and liquid oxygen. Okay, there are two pumps which is pumping the liquid methane and liquid oxygen, and the pressure at the end of the pump is 6.4 megapascal. So now the liquid oxygen is stored at pressure 2.4 megapascal, and liquid methane is stored at different pressure 0.8 megapascal. So they were asking us, so they have given few more uh, quantities, few more propellant characteristics, and they were asking us to find out what is the total mass flow rate through the nozzle. Okay, and what are the volume flow rates we are using for both liquid methane and liquid oxidizer. Okay, I mean here it's liquid oxygen, um, and what is the power required by the pump to feed liquid methane and liquid oxygen. Okay, so we are actually trying to find out what is the volume flow rate of these two, fuel and oxidizer, and also the pump power required. Okay, um, so let's first try to find out the mass flow rate. So how do we find the mass flow rate? So mass flow rate through the nozzle. So So let me try to write some given. So we have a mixture ratio to be 2.26. We have ISP is given, which is 2750 Newton second per kg, or you can also write this as meters per second. And then we have few properties of liquid methane, liquid CH4, and we have few properties of liquid oxygen. Okay, now liquid methane density is 424 kg per meter cube, and what is also given is the pressure at which it is stored, P CH4 is 0.8 megapascals, and what else is given? The thrust of the engine is given, which is 3000 kilonewton, and the burn time is 120 seconds. So density of liquid oxygen is 1141 kg per meter cube, and the pressure at which it is stored is 2.4 megapascal. I think pretty much I covered everything. Chamber pressure is given to be 6.4 megapascal. So first thing we need to find out is mass flow rate through the nozzle. I think this should be straightforward for you guys. How do we find out?
So, thrust upon ISP.
Wonderful. So it's going to be ISP is thrust per unit mass flow rate of the propellant. So mass flow rate of the propellant is equal to mass flow rate through the nozzle. That is the mass conservation we are studying. So this is going to be simply thrust. Actually, thrust I can write it as F. That is what we follow in the course. So thrust divided by ISP. Okay, so this is going to be 3000 into 10 power 3 newtons divided by 2750. How much is the mass flow rate coming out to be? Simple calculations. So I'm getting something like
1090.9.
1.0.
No,
1019.
1090.90 or
Yeah.
91.
Recurring 1090.9090
okay
goes on.
1090.90 kgs per second, right?
kg per second.
Yeah.
Wonderful. So yeah, this is straightforward. There's no problem here. So what is the volume flow rate of liquid methane and liquid oxidizer? Now we need to find out volume flow rate. How do we find out? Q of CH4, maybe Q dot, since it's a flow rate, Q of LOX. What information would be useful to find out?
We can divide the mass flow rate by the densities of the respective substances.
But for that you need to know
Right.
mass flow rate of CH4 and mass flow rate of LOX. This is with respect to CH4 and LOX, right? This is the total mass flow rate. It contains both CH4 and LOX. So they were asking separate volume flow rates.
No, since the mixture ratio is given, can we find out the mass flow rate of pure separate from here?
True, true. So that is what we are going to use. Wonderful. So it's going to be using mixture ratio. So what do we know about mixture ratio? It's a mass flow rate of oxidizer by mass flow rate of fuel, right? So we need to use mass flow rate of oxidizer, which is LOX, and divided by mass flow rate of fuel, which is CH4. We need to use this, and we also need to use the total mass flow rate, which is equal to mass flow rate of oxidizer plus mass flow rate of CH4. So these things we can use it to find what is m dot of LOX and m dot of CH4. Once you find m dot, as Pranav said, you can just divide it by density to find the Q of CH4 and Q of LOX. Okay, is that clear?
Yes, it's clear.
Alright, so let's see, it's mixture ratio is 2.26 is equal to m dot LOX. I think you guys can solve it and let me know. Just for the sake of completion, I'm just rewriting it. If you guys know the answer for mass flow rate, please let me know. So this can be written as 2.26 into m dot CH4. This is one equation, and the other equation is m dot LOX plus m dot CH4 is equal to 1090.9. So maybe you can substitute it here. So this becomes 3.26 m dot CH4 is equal to 1090.9. So m dot CH4 is equal to
7.6 for oxidizer mass flow rate is
okay
756.7
27.
756.7
Okay,
mass flow oxidizer.
right. And CH4, it should be 10 remaining
It's 334.631.
334.631. Wonderful. So this is what you will get as a mass flow rate. So now you can easily find the volume flow rate. Q dot of LOX is going to be simply m dot LOX by rho of LOX. So rho is given as 1141. So this is going to be 756.27 divided by 1141, and the Q dot of CH4 is going to be m dot into CH4 divided by rho of CH4. This is going to be 334.631 divided by 424.
For CH4, I got 0.7892
0.7892
meter cube per second.
meter cube per second. Wonderful. And for LOX,
LOX 0.662.
0.662. Alright,
662.
0.662, right?
Yes.
Okay, thank you.
Yes, sir.
So this is the volume flow rate. So this is also done, straightforward. You just need to use the mixture ratio. Mixture ratio will give us the idea of what is the rate at which these two are going. I mean, mixture ratio is a relative rate. So from there you can find the absolute values. Then finally you need to find out what is the power required for the pump to feed the liquid methane and oxidizer. Why we need a pump, and why we need to give some power to it?
because the fuel and oxidizer needs to like atomize and blend in so that uh, combustion take place in a very efficient way.
Okay, that is true, but this is separate pumps, right? So what do you have here is, okay, let's say if I can draw this. So you have a fuel tank and you have a oxidizer tank. This is CH4, this is LOX. Okay, and then what do we have is we have a pump for CH4. Maybe I will use red color for this, something like this. You have a pump for CH4, and then you have a pump for LOX, and then this thing is going into the combustion chamber, and then you have the nozzle. So we know the flow rate through these things, but my question is, what is we have separate pumps, and then you have injector here which is going to inject it. Okay, and the way it inject, it's going to make sure that it blends in and then combustion will happen effectively. But why do we have a pump in this setup?
Sir, for stimulating or making the process fast.
But you see the flow rate is same, right? The flow rate we say is, it's not going to change whether when it goes to the pump or not. See the basic, if you know the basic action of pump, what does this pump does, then you will be able to easily find out. What is
Sir,
that?
applying suction force.
Applying suction force, okay. Or basically you can say that you are almost right. Basically it pressurizes the fluid, right? When it goes through it, it gives additional power to the fluid so that it gets pressurized. For example, if you take a household pump, what does household pump give? It will give an additional energy so that it can reach the top of the uh, tank will be either, it will, if it is in the top of your house, so you need to give enough head so that you are trying to pump the water from lower to the top, right? For that, what you are doing, you're giving enough pressure so that it can get to that higher level. Here it's not really, you are not interested in head, what is the distance it's going to travel. Here you are interested in increasing the pressure inside the fuel and oxidizer. Because why? Because what we already know is, so the pressure in the chamber is given, right? What is the pressure in the chamber? It's 6.4 megapascal, and we need to operate at higher pressure, because higher pressure means higher performances in terms of C star. So basically C star depends on the pressure, right? Chamber pressure. So higher pressure means it's good for us. Okay, we need to have higher chamber pressure so that it will be efficient. So if you want a higher pressure here, then you cannot store everything at higher pressure, so you store at a lower pressure and use a pump to increase its pressure so that it reaches the chamber pressure, and then in the chamber pressure it reacts, and then it is going to give us a higher performance. So that's why you have a pump, that's why you have to do increase the pressure energy in the fluid, and that is what is also given. So basically it depends on the pressure. So what is the pressure given in the CH4? Actually it is 0.8 megapascal, and this is 2.4 megapascal. here the pressure is 2.4 megapascal, but the chamber is at 6.4 megapascal. So how will you reach that pressure? You have to use some pump to reach that pressure. Okay, if not, it will come at 2.4 megapascal. Your combustion will not be that much efficient. That is a problem. That's why people have to use pumps. There are different cycles as a way, different engines you might have studied, like blow down and feed through pump. All those things are like number one is you need to move the fluid from the tank to the combustion chamber. For that also you need some pressure difference in order to move it, and also it is better if you use a usually the chamber would be at a constant pressure, or you need to operate at a constant pressure, and so to supply fluid at constant pressures you need to use some pumps. Okay, that is the reason we use pumps. So now we need to is there any questions you wanted to ask regarding this? Okay, so if there are no questions, then how do we find the power of this pump? So we need to operate this pump. We need to give.
Can we say power is equal to pressure rise from 0.8 to 6.4, matching both multiplied by the volume of it.
Correct.
Right?
Yeah,
Multiplied
true.
by-
That is true. So the pressure given to the pump is going to be depending on the the power given to the pump is going to depend on what is the amount of energy you are trying to change, right? In this case you are trying to increase the pressure from 0.8 to 6.4. So that should be your that should be the amount of power the amount of power you give should be able to do that is the logic behind it. So it is not simply pressure times volume flow rate, it is actually the change in pressure times volume flow rate. Okay, so you will write the pump power of CH4 to be equal to the change in pressure. What is the delta P you are operating on? Change in pressure means, so basically from here to here, what is the pressure difference your pump is seeing? That is the delta P times the amount of volume flow rate of the fluid. Okay, so times Q dot into CH4. Similarly, the liquid oxygen also you can do that. So delta P of LOX and Q dot into CH4. So what is the change in pressure we are looking at for the methane? It is going to be from 0.8 to 6.4, right? So you should write this as 6.4 minus 0.8, and it is in megapascal, so please note down the units. So it should be into 10 power 6 times the volume flow rate of the methane. And similarly for oxygen, what you have to do, you have to take this 6.4 is the ultimate pressure minus the 2.4 is what you are going to give it as a pressure head you are going to give it to the pump. So this is going to be 6.4 minus 2.4. Is that clear? Into Q dot of, sorry, it should be LOX. So I hope it's clear, it's straightforward. So let's see, 0.7892 minus 0.8 into 10 power 6 into 0.7892. This is going to be 6.4 minus 2.4 into 10 power 6 into LOX is 0.662. 0.662. So what is the pump power we are expecting?
Yeah, for fuel, 4.4186 megawatts,
For fuel, it's 4.86.
4186,
4
or 4.42
4.42
megawatts.
megawatts. Okay.
For the oxidizer, it's 2.65 megawatts.
Okay. 2.65 megawatts. All right. So this is the ideal power you will give to this pump, but all the pumps will have its own efficiencies. For example, here it is not given. Uh, so in principle, this question we have already solved. So we found the pump required power of pump required to pump methane and liquid oxygen. So now my question is, let's say if I have some, there is always an efficiency involved with these mechanical systems, right? Let's say if I have some pump efficiency, let's say pump efficiency is same. Let's say it is 7 percentage. So then what is the real?
Divided by 0.7.
Right. So the reason is only 70% would be used, others are lost, right? So let's say if you need 4.42 megawatts, you need to give a higher power. So that is why, as sir said, you have to do, let's say this is P dash, let's say CH4 is going to be P of CH4 divided by efficiency of pump. So you can do this and you can find the ideal pump, real pump power required also. Alright. So is there any questions regarding this, regarding whatever we solved now? So today we are very quick in solving the problems.
Simple problems.
Right. So actually, I had a look at your week 9 assignments. So it was simple and straightforward. So that's why I thought, okay, let me solve one question related to that. Um, so I think you should be able to solve your week 9 questions without any problem. Mhm. Any questions you guys have? If not, we can move on to the second problem, which is interesting.
Actually, it's silly, but why was the burn duration given in the question?
Hmm.
Was there any like use of that thing?
So
Like
yeah,
they gave milliseconds.
right. So in this question, we never used burn duration. That is true. I think I took this question from one of the books. Maybe I avoided one of the question which should be useful. Yeah, in this question we are not using it. True.
Okay. Sir, are there any books like which you may recommend to solve things like similar questions like these?
So you can use the professor's book itself, Rocket Propulsion by K. Ramamurthy. That is what I use it for this class at least. So this book I have it with me.
Okay.
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 Or you can there are other books also. There is Saturn. There is one book called Rocket Propulsion by Saturn, Sutton. That also you can use, but it will be little more uh, theoretical and explanatory. That also you can use it to understand few concepts. Okay. So there is one interesting thought. I think I would like. I thought I will share it with you guys. So since you guys are doing rocket propulsion, so have you guys had a chance to go through this launch Starship flight test?
See, the last moment the signal got lost and while it was coming back,
Right, right, right.
it was
But
fine and
so if you guys haven't gone through this flight, it was very wonderful launch. In fact, it will give you a full. Uh,
what I noticed that this
mhm.
signal, the signal is because of EMP, the RAM effect, generation program. When plasma state and they accepted, expected signal loss for some time, it never got revived. Now, in this case, it's a very big rocket,
Mhm.
and they need to look at the design of those and then brand thing is also not to that extent. You could see in the video the plasma here or I don't know.
So
Investigate.
yeah, actually signal was lost. But the whole aim of this Starship flight test, this is a test flight. So the whole aim is to, reach the space and then return, re-entry, and then to land. But these guys are doing tests. They have a lot of money, so they just want to send rocket and burn. So they really when if you look at this flight, you will come to know. So I have attached the link also here. So if you look at this launch, let's say, so this launch, you will come to know that there will be places you will have. So you literally didn't have any. Uh, you can notice here, right? The methane and oxygen. You literally don't have any fuel for it to come and land. So they just want to leave it and let it go down. They want to collect data basically from this launches. So you will even see that there are no fuel and oxidizer left in the rocket, so there is no way it can land. But I personally like this full launch because it can. So the whole view itself is wonderful. They were able to capture it with a camera and they were able to have a live feed from there, so which is also wonderful. And also, if you since you guys are doing, I would recommend you guys to fully watch this launch. If you haven't,
You see,
it would be
this
interesting.
was showing this just a minute or second ago.
Mm-hmm.
Was showing.
Mm-hmm.
You saw that.
Which one?
It's this in,
Where exactly?
towards the end.
Mm-hmm.
It, see this glow. This is towards the end. No? It is coming with the tail down.
Right, right, right.
It's coming tail down, and
Mm.
from fins what is it? And the effect for the head.
Mm-hmm. Yeah.
And at some stage, when it was shown, right? Anyway, let us see.
So actually, you are breaking a little bit.
Okay, can be played at the end.
Okay, sure. Here.
Just carry on. This is some kind of. Is this the end part, or is this where the rocket is functioning?
Actually, this is the rocket is not functioning. The rocket is
Uh-huh.
entering. Rocket
Okay,
is
yes,
re-entering the atmosphere.
atmosphere. So on the re-entry, it is entering with the tail down. So
Mm-hmm.
that is the frontal part.
Right, right, right.
The tail is. If you enter like this,
Mm.
you are likely to burn the tail because that is not strong enough to withstand the temperature.
Right, but what they have is these black color
Tiles,
no
ceramic
ha
tiles.
tail is there. In addition, you have this black color. Basically, I don't know whether you were able to see
You
that.
see this at the fin tip, at the fin tip,
Mm-hmm.
there's a glow there. It starts, heating effect is much more there.
Correct, correct.
No, when if you have to enter, you should enter on a flat surface. Increase more drag, let the tube be. In this case, the bottom part is got a nozzle.
Mm-hmm.
So it is it is taking in the flow as it is coming down, vertically down at an angle. Uh, it should be rounded off at that point where it is entering into the atmosphere. Since it is not so, so the adverse effect of overheating, it's a plasma.
Mm-hmm.
It will be experienced much more in this area. They
Right.
should not enter it like this. They should enter like the space shuttle. On the body
Mm-hmm.
should be at an angle and then they should enter. It is a wrong entry. It's more like the fin trailing edge is not strong enough to withstand the high temperature.
Correct.
So obviously it was expected to burn. You see, plasma means more than 5,000 degrees centigrade
Correct.
temperature.
Correct.
It's mostly high temperature, more than 4,000, 5,000 of that order.
Mm-hmm.
And whatever insulation you have, so less likely to withstand the high temperature figures
Mm-hmm.
because it is not rounded off surface. The
Mm-hmm.
flow will get trapped inside it. The plasma will get trapped in the nozzle and that area is open. It's like a mouth.
Mm-hmm. Right. So.
So if it is coming at an angle,
Mm-hmm.
the body is facing the flow when it's coming down, the body can withstand it.
Correct.
This is my reading of the whole process. But they should have thought of it. They are so used to bringing their rockets vertically down,
Mm-hmm.
that they never probably thought of it. The space shuttle would not enter like this. Space shuttle will enter on the body at a high angle of that, with well-rounded leading edge course. That
Right.
would withstand.
So there is a difference between this and space shuttle. So space shuttle, what it has a flight kind of body. So actually, it comes and lands in the runway. But
No, I want to discuss about that.
okay.
Here also, the earlier tests we have seen from the vertical it became horizontal for a moment, it was flying like an aircraft.
Mhm.
Things are quite big, they provide the lift. So it could horizontally fly and then eventually became vertical with a tail down.
Mhm.
So re-entry is a long time. From
Right.
say 40 kilometers down to some 10 kilometers,
Mhm.
it has to come facing, generating the heat and withstanding the heat. After probably 10 kilometers, when they enter the colder part of the atmosphere, then they will make it vertical.
Mhm.
It
Actually,
should have not
right.
entered like this into the atmosphere.
Right. But here it's around altitude is around like 80 kilometers, right? So.
It is the Mach number at this point was 26,758 kilometers an hour.
Mhm.
And the Mach number must be around hypersonic speeds.
Right. So probably they are testing their insulation. So you would see that there is the lower bottom having this black color coating but not the upper part.
Yes.
So that also maybe I don't know what they are testing, but
Whatever. They
or
are
you can
like
also see this kind of boundary layer development because of this hypersonic re-entry. So that's why also you will see this kind of color also because of its high temperature, as you
high
said,
temperature.
plasma. You will have a high
It's
temperature.
white. It's nearly white. That's the
Ah.
highest.
Exactly. So yeah, I think they are testing different things. Only they will know why did they re-enter like that.
They have plenty of standbys available. Maybe next within a
Mhm.
month they will launch another one.
Mhm.
But it was quite a success. Such a big rocket.
Yeah, I think this is the
Big
first time it went outside the
Yes.
space and it came back.
They are going to more than 200 kilometers.
Mhm.
More than that.
Right.
They could have put it in the orbit also.
Right.
Low Earth orbit.
Yeah. Around almost they reached 95 kilometers. So it's
And
all
more.
more, right? Huh.
They can make more video
See, around 160 kilometers it went.
kilometers at this point.
200 kilometers.
200 kilometers, more than 200
Okay,
kilometers,
more than, yeah.
21.
Uh,
It's quite high.
right. Around
And
230 kilometers they have.
correct. 30.
And also what they did is they tested the satellite launch also from this. So they can
Yeah.
also launch a satellite from here. So they were at 200 kilometers if they want to launch a satellite. So
It
they
was
were
really cool.
trying to test. They opened that slide to launch a satellite, and they were testing that whether that works or not. So multiple testings they did actually. So in that way it's a
Quite
success.
successful.
Yeah.
Quite successful. One thing, unfortunately, they couldn't recover it.
Mm-hmm.
They recovered it, but success.
It's actually fully reusable, so that they have written it. So once it becomes a operational flight, it will become a fully reusable flight actually. So
Space
yeah.
makes sense.
Uh-huh. So this, yeah, I think you guys can have a look if some of you haven't watched this launch. It's a interesting thing to watch. So going forward, I have this one question. Before that, do anyone have any questions you wanted to ask? So I hope there are no questions. So if there are no questions, what we will do is we will try to use some you can say it as a software, or you can say it as a tool. Okay, basically it's a tool to find the chamber temperature, which is an essential quantity, and also characteristic velocity and specific impulse for any propellant you select. Okay, for example, this time I selected liquid methane and liquid oxygen. Okay, the same thing. Actually, this is what they use in the Starship also. This is the same propellant we used in the previous question also. So what we will do is, let's say for a given propellant, given liquid methane and oxygen, okay, let's try to find out the chamber pressure, chamber temperature, characteristic velocity and specific impulse. Okay, but what we are going to use is we are going to use something called NASA CE. So it's a freely available tool which I will demonstrate it now to you. So here CEA is nothing but, I think, chemical equilibrium analysis. Okay, so what we will do is we will use this tool. Okay, and for different mixture ratio, so for example, maybe I will read this: study the variation of chamber temperature, characteristic velocity and specific impulse with respect to the mixture ratio of okay, for the liquid rocket engine which operates on liquid methane and liquid oxygen. Okay, so for a different mixture ratio, let's say for set of mixture ratio, you try to find out which mixture ratio works better. That is what we are going to find out. Okay, and the initial temperature is given by the so initial temperature is the temperature at which you are storing your liquid methane and oxygen in the tank. Okay, so if we are not using any tools, if you want to solve it by yourself, how do we do it? We will select a mixture ratio, right? Let's say from the previous from previous question, let's say if I select to be 2.26, how will you do it? How will I find the chamber temperature? We already did this, right? 2 weeks back. So we have methane and we have oxygen, which gives us something, it gives, right? And then what do we do? We will say H of reactants equal to H of products and then from here we will find that T adiabatic. Basically we are trying to find out adiabatic flame temperature, that is the chamber temperature it will be, right? So this is how we do it. Is it clear, or am I missing something? Okay. So but the question is, what are the, so the same question I'm going to ask, what are the products you will consider? That is the question.
Sir, H2O and CO2.
CO2 and H2O. But the if the mixture ratio is stoichiometric, then you will get CO2 and H2O. But in real time, you will not expect it to be CO2 and H2O, right? In real situation, nothing like this will happen. In fact, you will have CO, as I said before, O. Even you will have a O atom, OH, H2, H, and then a lot of other things like this. See, you even have you can even have methane in it. But the problem is you do not have enough equations to solve. So you have only 3 atom balances, right? You have 3 atom balances, and you have lot of products. So just by atom balance you won't be able to solve it, right? Is it clear? The same question we addressed it earlier before. I'm just trying to remind it. So
that means if we find out from the mixture ratio, find out how many moles are there for O2, which is participating in the combustion process, which I calculate comes out to be 1.13.
Okay, 1.13.
Moles of oxygen. Okay, from there, if I try to balance the equation, now it's up to me what I'm going to consider in the product.
But the nature doesn't know.
Nature doesn't know. So that means what I'm calculating, considering my idea of the products being formed, that the adiabatic flame temperature may not be the correct flame temperature.
Exactly.
So going by this, all of the previous questions, the assignment, it is just an approximate guess.
True. It is true. That is the main reason we do not really rely on this. So it is for you to give an idea of what really happens. So the important thing you should note is, we did first law of thermodynamics. Okay, this is H reactant equal to H product is nothing but first law of thermodynamics, and we have atom balance, which is like a mass conservation. With these simple principles, we won't be able to get the adiabatic flame temperature. And something we are missing, and what we are missing is second law of thermodynamics. In this whole analysis, we did not consider second law at all, right? Did we ever consider the thermodynamics, entropy, whether the entropy of universe should be maximized, right? So, but in reality, entropy of universe is maximized only if you include that principle into your system. Whatever you calculate will be more accurate or more closer to the real system. So, but we never included this, and including this is a very complicated process, and it's not easy to teach it in a introductory level of rocket propulsion. That's why you might have given a little bit idea about equilibrium analysis, right, in the lectures, but in-depth analysis people don't go, because it actually falls in the realm of combustion. So if you take let's say a combustion course, you will know better about this. So that's why, and also by hand calculating is not very easy, because if you will select some variables and then you will hand calculate, but that temperature is not true, right? And the temperatures you are dealing with, the other problem is the temperatures you are dealing with is around 2000 to 3000 kelvins. In 2000 to 3000 kelvins, you will calculate that H2O, this much amount of moles of H2O is present. You might calculate it, but 2000 and 3000 kelvins are high temperature. This can undergo dissociation and it can form OH and H, or it can also form H2 only. So all these dissociation reactions can happen. So ideally you will never have H2O, or you will have less amount of H2O than you calculate uh, in the real systems. So you will not able to accurately predict the temperature. Okay, and that's why people use this highly sophisticated tools in order to find it. Let's see how we can solve it. So is there any questions till now? Okay, so if there are no questions, I hope you guys understood the motivation to use any tool.
These softwares EA of NASA,
Mm-hmm.
does it cover the aspects of secular thermodynamics, entropy maximization or something?
Right, so either you can say entropy of universe maximization, or you can say Gibbs free energy minimization.
Yes.
So they use minimization of Gibbs free energy actually. So let me also show that to you. So basically instead of so this second law of thermodynamics, actually they say it's called minimization of Gibbs free energy. So I would recommend you to read about this. How does second law of thermodynamics, which is delta S universe should always be greater than 0, can actually make give us to be delta G to be less than 0. Okay, minimization of Gibbs free energy, or minimization. So this is how then this NASA CEA tool is going to work. So let me show you, let me share my presentation here. So I think you guys will be are able to see my screen. Okay, so if you just search in Google NASA CEA, okay, so this will the first link would be the NASA CEA link. Okay, so were you guys able to see my screen? There is a CEA run.
Yes.
Okay, thank you. So in this you have different chemical problem types, chemical equilibrium problem types. The one we are interested is rocket. Okay, the others you feel free to explore other things. So basically this assigned enthalpy and pressure, we use it for finding the adiabatic flame temperature for any systems, not just rocket. And similarly you have shock tube, detonation, all these things that it's up to you to go through that. What we will use is we will use this rocket program, and there's some numeric code it requires this. So if you start this, you will have, one second, sorry, rocket. Okay, you select this, and then it will ask you for some pressure. Let's say for example we have 6.4 megapascals, which is like 64 bar. Okay, and then if you go forward, it will ask you to select a fuel. Okay, in the fuel you have lot of fuels here. Let's select methane, or if you want to have there are only methane, liquid methane, hydrogen. RP1 is a rocket propellant 1. Okay, and you have there is something called use periodic table also. So you can select periodic table if you want. So if you want something else. Okay, for us it's just liquid methane, so I could have selected there also, or you can select here also. Carbon and hydrogen would be the methane, and accept elements and selection. So you will have these many fuels available. In that we are interested in just methane. Where is methane? CH4 liquid, this one. Okay, and it is should be liquid, so that is why we have a parenthesis liquid. Okay, and let's say we go forward. You can add few more fuels also, but I have only one fuel liquid, and then proposition it's less so 100% proposition. Here they will ask for temperature, so the temperature we are going to give is 114, I guess. So the initial temperature is 110.64 is the temperature I am giving, and then you should select now oxidizer. Okay, the oxidizer here is going to be simply liquid oxygen, so we'll select that, and also liquid oxygen's temperature is also given 90.14. Okay, and then if you accept and select, then you will have mixture proportions. So what do we for the previous problem we did a mixture ratio of 2.26, right? So mixture ratio is nothing but oxidizer weight ratio by fuel weight, right? So mass of oxidizer by fuel mass of fuel, or mass flow rate of oxidizer by mass flow rate of fuel. So you can, so this O by F is nothing but our mixture ratio. So let's say we'll select 2.26. Okay, and now if you go forward, accept input and continue to the next form, there will be additional information about the exit condition. So basically till now you are given only the fuel and its initial temperature, and this is going to burn at certain pressure. That's what we have given. But if you want to know the ISP and C star, you also need to give some information about the throat. So either you can give it in terms of pressure ratio, or you can give it in terms of area ratio. Okay, for example, let's say I will give in supersonic area ratio to be something like 10. That is the area ratio I am looking for, that is the area ratio in my nozzle. So if we accept and continue, it will ask for a lot of things here. So there is this option called equilibrium, and there is this option called frozen. So what it does is, equilibrium is it does equilibrium calculations for the entire rocket. So in the combustion chamber also there will be equilibrium, but in nozzle and nozzle throat and nozzle exit, the temperatures will keep on varying, right? So because gas is expanding, so while it expands, it also does equilibrium calculation. That's why it is a equilibrium. For now we'll go with equilibrium. Let's assume that the reactions continuously happen and it attains equilibrium everywhere.
Just a question. There are two kinds of equilibria were mentioned by professor. One was the shifting equilibrium, another is frozen equilibrium. And that the frozen equilibrium occurs in the divergent part of the nozzle.
Right.
No, this frozen here also means that we are trying to find out the status of the divergent part of the nozzle.
Right, exactly. So this frozen option is the same thing. Okay, and if you select frozen, where you are going to freeze your mixture, you have to specify. There is this option 1, 2, 3, 4 and 5. So in this, actually 3 is the portion, 3 is actually throat. So for example, maybe you can read this manual. So there is this manual which says what is this 1, 2, 3 option. So let's see. So the same thing, whatever professor said, the same thing is what this is also. Let's see, where is that? Should be somewhere here. Subroutine rocket. So subroutine frozen. So here you can see that composition frozen at either combustion, which is option 1, at throat is option 2, or any downstream point that you want to specify, that will be more than 2. Okay, So basically, let's say if you select frozen and select 2, which means you are freezing your mixture composition at 2, and after that you are not allowing it to vary. And if you do that, then what is the performance we will be able to find. Okay, so it's the same thing whatever the professor says. So for now what we will do equilibrium, shifting equilibrium calculation itself. Okay, and you can see the parameters coming here. So the pressure we took it to be 64 bar, which is 6.4 megapascal. Oxidizer fuel ratio is nothing but the um, mixture ratio, which is 2.26, and supersonic area ratio is something like 10. Now if we do the CEA analysis, it will say just a click, okay, nothing else. So it will do whatever we do by hand, and it will show us the results. So you can go from here. Okay, so there are few informations of the program, and then you have this rocket, and then you have the pressure, which is 64 bar. These are the inputs we have given. This is also input, and you see that you selected the following fuels and oxidizer. This is also input, and then few informations they are giving it, and then finally we have theoretical rocket performance assuming equilibrium. Okay, so you see here, this is the fuel and oxidizer and its temperature, and then you have this kind of like a table. Okay, I hope you guys were able to see the table. So
Yes.
so you have a chamber, throat, and exit. Okay, so this is the 3 points in your rocket, and this is the pressure at the chamber which we gave, and we have pressure at the throat and the exit. Okay, this is what will have, this is the pressure will be at the throat and exit. Basically you can find this by doing all those complex equations that we derived during the nozzle chapter. And this temperature we have, chamber temperature, right? So temperature in the chamber is really your adiabatic flame temperature. Okay, this 2905.8 Kelvin is the adiabatic flame temperature that we calculate. But when we calculate, we just selected CO2 and H2O, right? But if you scroll down a little bit, you have mass fractions, right? In that CO2 you can see that's a very low amount, and H2O you can see only this. So whatever we calculated, we give utmost importance to only these two, but you can see there is a very high amount of CO present, and also you can see there is a O2, OH, O. All these things are like major species, which is what is this you will never be able to find out by doing a calculation. In fact, they are given only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So they have considered 11. They are showing 11 species, but you can say that there will be. So they have considered a lot more, and only these are the important species or major species in your system. That's why they are showing only the major species. So this is the most accurate calculation you will get, which is obviously will be more closer to the reality than whatever we calculate. Okay, so now
Sir, supposedly, if you alter the data, then the product's form will be different, or
Right.
it will be same.
Right, it will be different. So this is for a mixture ratio of 2.26, and at this temperature, what is the mixture composition? Now you can see for throat. At throat you have a slightly lesser temperature, right? Because the gases has expanded a little bit. So you have 2600 Kelvin, and for that also you can see a different composition. So you can see a little higher CO2 and little lesser CO, which means CO and O. So O2 has reduced and CO2 has increased, which means some recombination reactions have happened. Okay, and similarly you can see a little higher in hydrogen. So which means like higher temperature will always leads to dissociation like this, but a little lower temperature can help forming a recombination reaction and get us H2O. Okay, and similarly at the exit you can see the temperature is 1270 Kelvin, and at this point you can see a little more CO2. Okay, which means like lower the temperature, CO2, the recombinations can easily happen. But it is, if it is a higher temperature, all this CO2 will not remain as CO2, it will remain as CO and O. Okay, or H2O will not remain as H2O, it will remain as H and OH. Okay, so this is with respect to temperature. Now addressing your question, what we will do is we'll go back, and our interest is to, for a different mixture ratio, let's see which mixture ratio works better. We are interested in increasing this temperature, right? This temperature increase will lead to a higher performance. In fact, you can see the performance parameters. So this is the performance parameter. Okay, this is AE by A. This is nothing but A star, A by A star, or AE by A star. You can see at the exit we gave it as a 10 as an input. So you get the C star value of 1800 meters per second, and ISP is around 2926 meters per second, which is something like 300 seconds. Okay, now our interest is to have a very high ISP, higher C star, and also but higher ISP and higher C star is what we are interested, and the consequences you will end up having higher temperature. Okay, in the chamber. So what we will do is we will try to modify the mixture ratio and see what happens. Is everyone clear what we are
Oh,
doing?
yes.
Okay.
Yes.
Okay.
Okay, interesting.
So let's go back. So there is this oxide fuel which we wanted to change. You can give 30 points here. You can give 30 values here, or you can also give at a interval, so from low value to high value. So we started with the 2.26. Let's say we'll start with 1.5 to, let's say, 2.5. Okay, or we can go to 3 also. Okay, and the interval is something like, let's say we'll put 0.1. So you will have 15 data points. Okay, so now what we do, we will accept and continue to the next form. We will keep the supersonic area ratio to be same, and then you will see the inputs here. So you have 1.5, 1.6, 2, 3. Okay, you have like 16 data points which we can solve it together. Doing this by hand is a very big task. So let's continue. We'll still make the equilibrium assumption here. You can also give it a try when you are free. You can change it to frozen and run this simulation and see. So now again it gives us input file. Okay, and then you come here, there is a performance. So this is for oxidizer fuel ratio of 1.5, which is the mixture ratio of 1.5, and you see the temperature here, it's around 1672 Kelvin. Okay, so it was 2900 Kelvin for 2.26, but for oxidizer fuel ratio of 1.5 it is 1672 Kelvin. And if you scroll down, since the temperature is less, you will have these as your mixture composition. You have something called CGR. I don't know what is that. You can look at you can look at this. What is this?
Oh, carbon graphite,
Probably, yeah, carbon. Carbon can also stay like carbon.
the pure state of carbon.
So and then you have formaldehyde, and yeah, so a lot of things you have. So this composition also changes with respect to mixture ratio, which we know. And important thing is we are interested in performance, and you see the performance C star here is 1500 meters per second, and ISP is 2478. So basically it's a bad mixture ratio. This is not the mixture ratio you should select, right? So and then you go down here. Here you have mixture ratio of 1.6. Let's look at ISP. We'll decide with ISP. ISP gives us a complete picture. Okay, so ISP is 2549. Previously it was 2400. Now it is 2549. Still not good, because 2.26 was 2900. So for oxidizer fuel ratio of 1.7, your ISP is 2600. So it is keep on increasing, you can see, right? And for 1.8 you will have 2693, which is okay. And then for 1.9 you have 2700, 2760. Okay, and for 2 you have 2816, and then for 2.1 you have 2864, and for 2.2 you have something like 2900. This is the same thing that we got for 2.26, right? So now you are 2900. This is the highest. Let's see where it goes. For 2.3 you have 2939. Okay, 2.3 is better. 2.4 is 2968, which is also better. And then 2.5 is 2992. 2.5 looks even better. You have 3000 also. 2.6. Let's see where it goes. 3026 and 3036. You see the increment is reducing. It's not very big. And then at 3042, good. 3043. See, from 2.9 to 3, it's
I have a
3000.
question.
Hmm.
I have a question.
Hmm.
No, this is with respect to mass ratio.
Mixture ratio. Yeah.
The range that we have specified is giving us the various parameters.
Hmm.
Can we get the plots also with the MR on the x-axis and the parameters on the y-axis? So
Actually-
then we can find out the maxima for each variable.
Actually, this does not give you this; just gives you the value. We only have to plot it separately.
Okay.
So 3.3 looks better. So what I will do is I will increase to 3.5. Okay. Let's see. I want to see which is the highest. So let me do this calculation again. It's not like it will take a lot of time. It's just you press the button, it will give you the answer. So let's go to 3. So 3 is 3043, and 3.1 is 3041. See, so this is the highest. 3043.8 is the highest. So which is at 3. So are somewhere between 3 to 3.1. Somewhere between that you will have 3000 as your ISP, meters per second as your ISP. So if it is 3000, okay, this is the highest ISP. So now you check the temperature of this. It's 3458. So that is it's a very high temperature, right? And you check the mass fractions here, and you will see the mass fraction of CO is higher than CO2. Okay, but somehow H2O remained as H2O. This is in terms of mass fraction, so it might be misleading. Maybe if you change it to mole fraction, you will know better. Okay. So anyway, we have highest ISP here, which is 3043, and for which you have temperature is 3458 Kelvin. Now let's say if I go little less, 3042, you will have 3458. You have temperature decreasing. Okay. So which means higher temperature actually coinciding with higher ISP. Now look at this. So we have oxidizer fuel ratio of 3, which gives us higher temperature. I mean the temperature is 3458 and the higher ISP 3043. Now let's go to 3.1. Okay, 3.1 has lesser ISP 3041, even though not much less, but 2 seconds less or 2 meters per second less. But you see temperature is high, 3488. Before previously it was 3458, here it was 3488. So the peak in temperature with respect to mixture ratio and peak in ISP with respect to mixture ratio is not the same. Okay, which means the ISP is actually affected by these dissociations happening in the in the mixture composition. So these are few things you can observe from this kind of analysis, which gives you good thoughts. So in fact, if you go to 3.2, okay, in 3.2, so all these are becoming equivalence ratio is 1.24, which means it's becoming fuel lean. Okay, which means lot of oxidizer is present. So at 3.4 you have 3500 Kelvin, which is greater than previous temperatures, but ISP is less. So which means higher temperature is not really you would expect, because of these higher temperatures will not directly correlate it to a highest performance because of this dissociation. That is what I wanted to specify here. You can see a lot of dissociations happen. Okay, and then if you go a little further, again 3500, you will see a very poor performance even at higher temperature. So higher temperature is not ideally higher performance, even though it can we can correlate it, but the peaks are different. So that is the reality actually happens, which I wanted to show. So any doubts you guys have at this point? Okay, we have a question. Why ISP as unit meters per second? It should be Newton second per kg. Actually, both are same. If you look at it, if Newton second per kg, if you expand Newton, it will give you in meters per second at the end of the day. So you can either use meters per second or Newton second per kg. I hope that clears your doubt. So what else you can do is, I will show you other things also. So we changed mixture ratio in this way, right? We changed the mixture ratio here. What we can also do is we can change the pressure. So we did only for 64 megapascals. You can change the pressure and see what is its effects. So in that way you can modify it. You can run your chamber, you can run your rocket at a constant pressure of, let's say, whichever gives you highest ISP. So this is how you select the parameter of chamber pressure. And if you select that chamber pressure, similarly you need to select the pumps. The pumps is going to pump the liquid methane and the liquid oxygen into your system. So you need to select that pump. So the power to the pump also will increase when you increase the pressure. So it is you see lot of variables will come together, and you have to, if you are selecting it, you have to be very careful, because you cannot give infinite power to the pump. So it's actually a sweet spot between pump power, how much you can give, and also the rocket performance. Okay, so you can change this
Sir,
pressure.
I don't understand the difference between shifting equilibrium and frozen.
Okay, I will tell you. So by the way, are you guys good with this tool? Can I stop presenting it? So I hope you guys understood it. Ram sir, I think there is a echo from your side. So for now, maybe I will mute. You can unmute so you can unmute to ask your questions. So let me share the screen from here. All right. So let me address Tanisha's question. What do we have here is you have this rocket, and then you have nozzle. Okay, and the temperature here is going to be adiabatic flame temperature, and as the flow goes, the temperature will keep on getting reduced. So it will be something like this, right? So now the gases present here, let's say O2, H2, OH, CO, CO2, and a lot of things will be based on the that temperature, adiabatic flame temperature. Okay. Now, let's say if this reduces, your equilibrium also shifts. So as temperature reduces, the CO2, whatever the CO2 comes, whatever the CO2 coming here, CO and let's say O coming here, since temperature decreases, it can actually become meet and become CO2. Okay, but only if it becomes in equilibrium. But whether it will become equilibrium or not, that we don't know. But you can say that either it can become equilibrium or it can just stay at CO and O. Okay, so the if it just stays as CO and O, then it's frozen. Okay, and there is a possibility that either it can become CO2 or it can just stay. The only possibility is between either it will be in equilibrium or it will be in frozen. Okay, um, this is the two extremes in this situation. You can be anywhere in between this. So that's why we have two options: equilibrium and frozen. You do your analysis for equilibrium, you get your performance. You do your analysis for frozen, get your performance, and your real rocket's performance is going to lie between these two. Okay, that's why we have this two different analysis. So this the mixture composition you have here and the temperature is what is going to affect the performances, ISP C stars. Okay, so that's why either you do equilibrium analysis, tell that it can attain equilibrium everywhere in the nozzle, or you say it will not attain equilibrium, it will stay whatever comes here, it will stay as it is as it goes through the nozzle. So basically there won't be any recombination reactions happening. If you say like that, it's a frozen. If you don't say, if you allow it to equilibrate, then it's a equilibrium analysis. Is that clear? Did I address your question?
Yes, sir.
Okay. So basically what I was also telling is, let's say you have a mixture ratio plot. Okay, mixture ratio with respect to adiabatic flame temperature, or let's say ISP. Okay, now if you do a what do you call equilibrium analysis, you might have something like this. Okay, this must be, let's say, equilibrium analysis. And let's say if you do a frozen analysis, your performance would be slightly lesser. This might be your frozen. Okay, and your real rocket performance will lie somewhere in between. Okay, that's why they have two options, so that you will understand that what is the range in which my real rocket is going to operate. This range can be very low, so it can be in the range of like let's say if you are talking in ISP, let's say it can be in the range of 10 meters per second, or 20 meters per second. But that is better than what we do doing hand calculation. We might be off by hundreds, even 50 meters per second in terms of ISP, and in terms of temperature we might be off by like 500 kelvins, 500 or 1000 kelvins. Okay, because we simply don't consider that there is a recombination reactions happen, dissociation reactions happen, and also we do not consider all these uh, species in our mixture. We consider only we are good with only CO2 and H2O. Okay, any other questions?
I had a question which I said I'll ask in the end.
Yeah, please. Yeah, please.
Assignment.
Yeah.
Can you open the assignment 8?
Week 8.
I've written this assignment. If you look at question 11, there is the data given there.
This one?
I have also opened this. Yeah, this data. If we read it, it says radially outward and inward burning solid composite propellant grain is designed as shown below.
Mm-hmm.
and the grain is shown there.
Correct.
Normally, what we are discussing in the class and as a convention, we will consider that the outer grain is burning radially outwards, and the inner grain is burning radially inward.
Correct.
Right. That is the convention. From the statements that is written there,
Mm-hmm.
one could also consider that the two grains are, the outer grain is not case bonded to the combustion chamber, and it could also burn radially inward. That is one of the possibilities which is not clarified in the statement.
So, radially burning solid composite propellant grain is designed as shown below.
If it was said that the case bonded grain,
Mm-hmm.
then the situation would have been clear.
How about this one? This one has composite propellant. Burning of propellant starts from the initial port
This
volume.
has to start from the inside only.
Yeah, there is no outside. So then means I was first confused, like which is grain, whether white is grain or
No, yellow is
yellow
the
is
grain.
grain. Okay.
Yellow should be the grain.
Now yellow is the grain. That is clear. So now they have said it's a radially outward and inward solid composite propellant grain. So which means
The outer grain
mhm,
is burning radially outwards
Correct.
progressively.
Correct, correct.
That is what is conventional thinking.
Mm.
From the statement, you could also decipher it as burning both ways, inward as well as outside, from outside to inside.
So I don't think so that is the case. So why they say outward and inward is you have like a two strands of grain, right? So you have a center cylinder also,
that is
and
burning
also you have a
inwards.
hollow. The center cylinder is burning inwards. The outer hollow is burning outwards. So that's what they said as they added these two as a one grain. That's why they say as it's radially outward and radially inward also. I think that is how you should see this question.
Okay, that just by the way.
Mm.
But my point is different. Another point question is, when I do this question 13, when I try to solve it
Mm.
and use that formula, the combustion pressure, that is equalized pressure or
Equilibrium
whatever,
pressure.
equilibrium pressure is equal to rho P into SB
Mm.
into A into C star divided by delta T
Mm.
to the power 1 over 1 minus N.
Right.
When I do the calculations, I find the pressure is coming to be exorbitantly high. It is 1 lakh megapascals.
Yes, sir.
I see.
She's also feeling the same way.
I see.
Maybe the units of A,
Mm.
we would like to know.
Okay. Okay.
I'm
Okay.
not getting the right thing here.
Okay. So
It so
probably
happens.
let me
Can
quickly
we
try.
do the calculations? It's a simple calculation.
Right.
Rho P is 1850.
Mm-hmm. But we can. What is the burning time you are getting? Let's say 1 lakh.
No, time is
1 lakh
not
pressure,
important.
right? What is 1 lakh megapascal?
Oh, burning time is the fraction of a second. It's like explosion.
I see. So may I know the pressure you got? Initial pressure?
Or sir, either white portion is a grain.
White portion.
No,
See,
can't
if
be
white
grain.
portion is a grain, means then here they cannot shift the convention, right? In the second question they have in the second question what it was shown, initial port volume which has a square cross section. So it's a port volume, so it's a square cross section. So
It's a square.
that is a empty.
That
White is
a-
actually empty.
The port is square in cross section.
Which means it's
Whereas-
empty. That's not the grain.
This is empty.
Which means
So,
here
going
also
by the
there should
same
be.
convention.
They should be same convention only they will follow. And also for a grain we usually give a different color. So uh, yellow is the I feel is the right, I think.
Yeah. So if we accept that, then
So
the combustion chamber pressure is exorbitantly high.
how
Can you solve
much
it?
how much is the pressure you guys are getting? Let's say
I
one
am getting, the others can say, 10 lakhs
10 lakh
uh,
megapascals.
on a 1 lakh megapascals.
Okay, 1 lakh megapascals. Let's see if I can quickly find what is the burning rate for this.
Approximately, you can approximately calculate. 1850 multiplied by, I have calculated burning area as 6.79 meters square. Oh no, I am telling the answers. It is from another question 11.
I see. So it looks like burning rate is 24.54 mm per second. So burning rate is in mm per second. Have you taken that into account?
Where is the burning rate? Is it given here?
Linear burn rate law of propellant is mm per second.
No,
Is
it is
given
given,
by-
value of A is given, value of N is given.
But burning rate is in mm per second, right?
Correct, that is not given.
So I think I understood where the problem is. So what I would suggest is
Okay, I
you do the
I
math
got it.
properly.
Yeah, I got it. Understood.
I think Tanisha, you also should do the math properly.
Uh,
So see what is the units of burning rate. Okay, it's not in meters per second. You should know whether the formula you solved did it take R to be in meters per second. Or
millimeter.
you should know the what do you call the units of A and units of N. I mean N will not have unit, but you should know the units of A.
No, A cannot, this point was discussed in the class also. A is a constant, and unless we consider this as a reference burning rate.
Actually, A does have a unit. A cannot be unitless.
Oh,
So if
Yeah.
A is unitless, then you will never match R is equal to APN. R is in meters per second. If A
No,
is
what-
unitless, P is in pressure. Right? There is no way we will be able to match the
Dimensions
left-hand
both
side
side.
dimensions. Right. So A
No.
does have a unit.
correct, that A becomes meters per second divided by pascals to the power N.
Yeah, exactly.
Can we consider this as a complex description of a unit?
So basically the A is obtained from the experimental data, so people can still be like people does use it like that. It is true.
Okay.
People
And
does use it like that.
So P is in pascals, and A, that way we'll have to find out what unit.
Which unit it is in? If you should convert it to a proper unit and then you should substitute it.
Proper unit.
So then I think you will be able to get
So let
proper
me try
results.
that. There are plenty of questions where the PC has to be found out. There are other questions also, and everywhere I was getting exorbitantly high chamber pressure because it was there in my mind that I should use the value of A properly.
True.
I am not using the value of A properly,
Right.
so I will have to have some factor multiplying with that,
Mm-hmm.
converting this to proper units. Okay.
Any other questions?
I don't know whether other students are also face the same difficulty. Maybe they have resolved the problem. Okay, no more questions from me.
Thank you.
Okay, thank you.
Any other questions does Pranav or Balu has?
No, sir, no.
Thank you. So anyway, if thank you, Balu. So you can stay back and ask if you have any questions. I will be here for some time, or we can meet next class. Thank you.
Okay, I'll
Thank
be
you for
leaving.
attending.
Thank you. Thank you.
Thank you.
Thank you, sir.
Thank you, Pranav.